Hi everyone, myself Dr. Rama Devi, Professor of IT Department, Ministry of Aeronautical Engineering. Today's topic is logic and propositional calculus. Okay, in that our topic is propositional logic. First, what do you mean by mathematical logic? Okay, based on that, we can define what is the proposition and how we are framing one logic based on that. Okay, in this mathematical logic, first, what do you mean by logic? Logic is the study of relationships between objects and forms. Objects and forms the basis of all mathematical reasoning and all automated reasoning. The study of logic in mathematics is called the mathematical logic. Here we are having some mathematical logic we are using. Conjunction, disjunction and negation. Conjunction we are defining as this cap symbol, and disjunction just we are representing with like it seems like V, and negation, this is the symbol we are using for negation. Some other mathematical logics are implemented and double implications. Okay, based on that, here I can define what do you mean by the propositional logic. Propositional logic is also called the propositional calculus and sentential logic. In propositional logic, the objects are called the propositions. The objects are all called the propositions. Okay, a proposition is the statement that is either true or false, but not both. Yes, a proposition, that is one statement. Like here I am defining one proposition, one statement, that is today is Monday. Yes, that statement, if it is either true, then we can say that that is true, or if it is today is not Monday, then we can say that that statement is false. But it is not, but not both. But not both means true or false, both conditions does not applicable to one proposition. So a proposition is the statement that is either true or false, but not both. We usually denote all the propositions by the letters P, Q, R, S, A, B, C, D, like that. We can represent the propositions by letters, alphabets. Okay, the propositions are mainly of two types: atomic propositions and compound propositions. Here we are having two types of the propositions. Okay, propositional logic is also equal to the propositional calculus. That can also we are calling it as the sentential logic. That is the statement, if we are defining either that is the true or false, but not both. Yeah, the value of the proposition is called its truth value. The values of the propositions we are saying it, the statement is either true or false. If it is true, we are representing as true. If it is false, we are indicating with F. If it is true, we are replacing it with 1. If it is false, just we are putting it as 0. The value of the proposition is called a truth value. Truth value means that value, it may be either, if it is true, true we are representing with T. In false, we are representing with F. Okay, whatever the representations it may be, but the value, if either it is a true value or if it is a false value, whatever it may be, the value which we are representing in the proposition is called the truth value. Here we are denoting T, truth value T. Truth value T means that its value is true. That yes, like one example, today is Monday. Yes, today is Monday. That is the true statement. So the true statement we are representing with T or 1. False statement. The false statement we are representing with F or 0. That is today is not Monday. Today is Monday, but today is not Monday. In that case, we can represent the actual day is not Monday. So that statement is false, like that. And we are also here, we are having some opinions we may have, some interrogative sentences we may have, and imperative sentences we may have. All these are all not propositions. So the opinions, we may have some opinion. She is good, he is good, like that. I have one opinion. That is not a proposition. The proposition that is a statement. it must be either true or false. Yes, if it is true, then we can say that it is true. 2 plus 3 equal to 5. That is always true. 2 plus 3 equal to 5. This is the true statement. So this is a proposition. Today is Sunday. That is the proposition. Today is Monday. That is the proposition. Like that, we are declaring one sentence. That is the statement. But it may be either true or false. That condition may be, in some cases it may be true, or in some cases it may be false. That such type of statements are called the propositions. Okay, opinions, interrogative sentences and imperative sentences are not the propositions. Here we have some examples of what are the propositions and what are not propositions. Yes, today is Monday. Monday, the letter we are representing with M, capital letter. M-O-N-D-O-Y, Monday. So, the day beginning with the word beginning with M. So, we are representing with M. The grass is wet. Yes, we declared it. The grass is wet. We don't know either it may be wet or not. But we declared the one sentence. At the beginning wet, that sentence is W. It is raining. Yes, in this we are having raining R. So, we are representing with R. These are all the propositions. It is raining. Just we declared it. We don't know whether it is raining or not. But just we declared it. It is raining. So all declarative statements, the propositions are all the statements. See the next example. The following are not propositions. Yes, C++ is a best language. This is the opinion. Some people they may told Java is the best language. Some people they may follow C is the best language. Some people they may follow .NET. Some people Python, like that. Each person they have their own individual opinions. So we can say that C++ is a best language. This is not the proposition. We can't say C++ is the best language. This is just our opinion only. Next one is, when is the pretest? Yes, when is the pretest? I am asking the question. When is the pretest? Okay, that is the interrogative question. This is also not the statement. So, this is not the proposition. Just one is, do your homework. Yes, I am saying you, do your homework. This is not the proposition. This is not a statement. I told you, do your homework. This is the imperative sentence. Okay, like the sentences which are having the opinions, interrogative and imperative, these are all not the propositions. So the proposition is one statement. We are defining it. Either it may be true or false. Just like the examples. Today is Monday. Yes, that is one declarative sentence. But we are not sure today is Monday or not. Either it is true or false. But today is Monday. This is one statement. The grass is wet. We are not sure the grass is wet or dry. But we declared it. Today the grass is wet. So that is one proposition. The next one is, it is raining. We are not sure it is raining or not. But that is one statement. It is raining. Like that. All the statements we can declare it. Either it may be true or false. Is called a proposition. The remaining all opinions, interrogative sentences, imperative sentences, these are all not the propositions. Okay. Here we are having some notations to denote the connectives. The logic in here we are having some atomic values and composite propositions we have. Yeah, connectives are used to create the compound propositions from two or more propositions. Connectives. We are using the connectives to connect two or the more sentences. Today is Sunday and holiday. Yes, here we have one sentence, connection, that is and. Today is Sunday and holiday. Yes, this is one sentence. Okay, in this here we used and operation. And. Yes, to connect these two statements. Today is Sunday. The two statements are, today is Sunday. Today is holiday. These are the two statements. This is one statement and this is the second statement. By combining these two statements, we are calling it as the composite proposition. To create one composite proposition from two or more propositions. This is one proposition and this is one proposition. Today is Sunday, that is one proposition. And at the same time, today is holiday, that is also one proposition. By combining these two or more propositions, here I used and operation. Today is Sunday and holiday. So here we have some connectives are used to create the compound propositions. Those connectives are negation. Today is Monday. Today is no holiday. Yes, here we have some negation. And operation or logical connection. The negations, here we are representing negations or negation of A. This is one representation. This is also another representation for negation of A. A bar, this is also one of the representations for negation. Next one is and or logical conjunction. Conjunction means we are connecting the two statements. That is the and operation. By having and operation, with and operation we can able to connect two logical statements. So we are calling it as the and operation or logical conjunction. Just we are denoting that symbol by and operation by cap symbol. The next one is or operation or logical disjunction. Disjunction means we are disconnecting the symbols, notations. We are disconnecting the propositions. For that purpose here we are calling it as the logical disjunction. The operation we are using as the or, and we are denoted it by like V operation. Next, that is the opposite to the and operation. Next one is the exclusive or XOR operation. XOR operation, that is also called the exclusive OR operation. Exclusively OR. That is denoted with that plus symbol with circle, surrounded by circle. The next one is the implication symbol. That implication we are defining with only, representing with only the arrow mark, or with, this is also we can represent biconditional. That is the bidirectional. We can represent like this, or we can represent like this also, with single arrow or with two arrows. Yes, we define the meanings of the logical connectives using the truth tables. We define the meanings, semantics of the logic connectives using the truth tables. The table, yes, here we are having some connectives. This is the logical AND operation, this is OR operation, this is exclusive OR, this is NOT operation, negation operation. Yes, we are having all these operations. Okay, to represent, to define all these meaning, to define the meaning of the logical connectives, we can represent by using the truth tables. Truth tables, we can represent it. Next one is the precedence of the logical connectives. Yes, first for what we need to give priority. Based on the equations, we need to prioritize them. Okay, as in arithmetic, an ordering is imposed on the use of the logical operators in compound propositions. Compound proposition means we are combining two or more propositions. Okay, however, it is preferable to use the parentheses to disambiguate operators and facilitate readability. Here we are having one example. This symbol we know, this is the negation of P. This is the R operation, and this is Q. This is the AND operation, logical AND operation. We are calling it as the R operation. This is the disjunction operation, AND operation, that is the conjunction operation. This is negation operation. Yes, the negation we are representing like this or just like this, not. Okay, we can represent in any of the forms. Here we have an example. That example is negation of P, R, Q and negation of R. Yes, we need to compute. If we want to compute this problem, we need to know first what are the Propositions I need to collect. Okay, for that, here we have, first we collected negation of P, R operation. Next, Q and yes, negation R value we need to find out. Next, we need to enclose all these with some parentheses. Okay, to avoid all these unnecessary parentheses, here we are having, first we are computing negation of R. And for this we are having some parentheses. Negation of P directly we can compute. So no need to apply parentheses for that. Okay, we need to avoid all these confusions, unnecessary parentheses. Here we need to follow some precedence rule. First we need to apply negation, next conjunction, next disjunction, next implication, and next biconditional. To follow the precedence rule, first we need to apply parenthesis for negation. How we apply this negation of R or negation of P value. Next conjunction for these two connecting with the two. Next again disjunction operation. This is the disjunction operation. We are applying operation on that. Next the implication. Okay, in this example we don't have here any implication. We need to follow the implication, and next one is the biconditional. By following these precedents, then we can easily operate all the propositions. How we are, one BODMAS rule is there in our mathematics. Like here also we need to follow this, that is brackets of division, multiplication, addition and subtraction. How we are following to get disambiguity to operate our operations. Okay, similarly here also in the propositions we need to follow the some precedents for our all logical connectives. First we need to apply negation, next for conjunction, next for disjunction, the fourth one is the implication operation, next one is the biconditional operation. Like that we need to apply precedents of our all logical connectives. Yes, first here we are told all the propositions we are representing in the form of the truth table. Truth table means the table which we want to represent in the form of one tabular representation. The logical identity is an operation on one logical value. In this we are having the logical identity. Identity means here we are having only the one value. That value, if I am considering one value, that value it may be, in one case it may be true, in some cases it may be false. Okay, the logical identity is an operation on one logical value. Typically the value of the proposition that produces a value of true if its operation is true. Here we are having some value P. I considered one value P. Yes, this is the output. This is our result. This is our result. This is the input here we are giving. Yes, the input proposition. I am giving one proposition. Today is Monday. Yes, I am representing the value as T. Today is Monday. The result is yes, true. That is true. Yes, today is not Monday. Then the result is not. Like that. The logical identity is an operation on one logical value. Typically, the value of the proposition that produces a value of true if its operand is true, and the value of false if its operand is false. The truth table for the logical identity is logical identity truth table. We are representing, we are giving some input values and we are getting some result values. We are giving the values as T. If it is T, identity, only here we are having one value. If this is true, this is also true. This is false, then this is also false. Next one is logical negation. We know negation. Negation is the operation on one logical value. Typically, the value of the proposition produces a value of true if its operation is false. And the value of a false if its operand is true. The truth table for not. This is the negation. Yes, I am saying today is Monday, but today is not Monday. So negation. Negation value means yes, not that the same result. For F, we are having the T. If it is T, we are reflecting with F. If it is false, we are having the T. truth value as T. These are the truth values. The value it may be either T or F. Yes, the next one is the logical conjunction operation. Conjunction means conjunction of two propositions. Here we are having one statement. P is one statement. P is one statement. Q is also second statement. Yes, here we are having the two statements. P and Q is the statement. Now we need to combine these two statements. So we are having some conjunctions we are using here. The conjunction of the two statements, P and Q is the statement. Yes, P and Q, the AND operation we are representing with the cap, which is read as this cap, that is the operation. Here we are reading it as P and Q. The statement P and Q has the truth value T whenever both P and Q have the truth value T. Otherwise, it has truth value F. Yes, here we are having ST value can be represented with 1 also. We know PQ, P and Q. This is the truth table for this conjunction operation. Yes, P value 1, Q value 1. P value 1, Q value 1. That is, here we are having result also 1. The both statements. If today is Sunday and today is holiday. So I am combining these two statements. Today is Sunday and holiday. So that is its resultant value is also true. The next one is 1, 0. 1, 0. Its value is 0. 0, 1. Its value is 0. 0, 0. Its value is 0. The statements whenever both P and Q have the truth value as T. Yes, in this table, P value and Q value both are having the truth value as T. In this case only, here we have the resultant value, the logical conjunction, the conjunction of P and Q. That is true. In remaining all the cases, we are having F, F, F. TF, the result is false. FF, FT, the result is false. FF, the result is false. Here we are having the 4 connections. PQ. Since the variables here we are having P and Q are the 2 variables. So for these 2 variables, we can have 2 power n combinations. Okay, 2 square combinations. The variables are, here we are having the 2 variables. For these 2 variables, here we are having the 2 power n. So 4 combinations we will get. 4 combinations are T, T, the result is T. True, false, the result is false. False, true, the result is false. False, false, the result is also false. Here total combinations are 2 power n combinations we have. For that, the value, if here we are having n value as 2, so we are having the 4 possible combinations. Those 4 possible combinations are, these are the 4 possible combinations. TT is resultant is F. TF, the result is F. FT, the result is F. FF, the result is F. Like that, we have here 4 combinations. If the number of variables here we are having 3, that is 2 cube. So in that case, we may have 8 possible combinations. Consider here one example. Consider the following statement. Here we are having the 2 statements. P is one statement and Q is also one statement. The P statement is, it is raining today. Yes, we don't know either the statement is true or false. That is one statement we declared it. Yes, it is raining today. The next Q statement is, there are 10 chairs in the room. Yes, this is also one statement. We don't know 10 chairs are present or 12 chairs are present. But whatever it may be, there are 10 chairs in the room. We declared it. We told that. That is one proposition. Then we need to combine these 2 statements. P and Q statements, we need to combine them. How we can combine? It is raining today and there are 10 chairs in the room. Yes, here we have some logical connectivity between these two propositions. For P propositions, it is raining today. And for Q proposition, there are 10 chairs in the room. So by combining these two, P and Q, we can declare that it is raining today and there are 10 chairs in the room. Here we used one connective, that is the AND operation. This is one logical conjunction. Usually in our daily language, the conjunction AND is used between the two statements to define any of the some kind of relationship. It is raining today and 1 plus 1 equal to 2. It sounds odd, but in the logic, it is preferably acceptable statement and formed from the statements. It is raining today and 1 plus 1 equal to 2. Yes, we can combine these two. Next example is Jock and Jill went up the hill into the symbolic form using the conjunction. Translate. This is the statement they have given. Here we have AND operation. Translate them into the, this is one symbolic conjunction statement. We need to translate into the symbolic form. Yes, Jock and Jill. Here we are having the two sentences. Jock and Jill went up the hill. So the solution for this problem is, here we need to declare two statements. These statements are PQ. The P statement is Jock went up the hill and Jill also went up the hill. Jock, Jill. Here we are having the two persons. These two went up the hill. Okay, by combining these two, here we have one sentence. The solution for this statement is Jock went up the hill, Jill went up the hill. So by combining them, we can say that Jock and Jill went up the hill. Then the given statement can be written symbolic form as P and Q. Yes, Jock went up the hill and Jill also went up the hill. P and Q. That is in the symbolic form. This is in the statement form. By combining these two, Jock and Jill went up the hill. That is our statement by having the logical conjunction. Like that, we can combine any of the sentences. Yes, the next one is logical disjunction. The logical disjunction is an operation on two logical values. Here we are having the logical disjunction symbol, we are representing with OR operation. So the logical values here we are having P and Q are the two propositions. Two propositions, P is one proposition, Q is one proposition. Now we need to combine these two, the disjunction operation P or Q. Just that produces a value T. The values here we are having the P and Q are the two variables. So the number of possible combinations are, for two variables we are having 2 square. So that is 4 combinations we may get. Those 4 combinations are PQ 11, 10, 01, 00. These are the 4 combinations we may get. Okay, by combining these two, the disjunction operation PRQ is the PRQ value. If both the symbols are true, then the result is also true. If both the statements, one of the statements is true and another one is false, in that case also we are getting the result as true. If one of the sentence is false and next sentence is true, in that case also we are getting the result as true. If both the sentences are false, that is FF. In that case, just we are having result as F. Okay, like that. The logical disjunction is an operation on two logical values. Typically, the values of two propositions. Here we are having the two propositions P and Q. And produces a value true if at least one of the operands is true. Here the one of the operands is, these are the combinations. This is true. Then the result is also true. One of the operations, this is true here. So the result is true. This is, even though these two are false, but the result we are getting as T. If this is F, this is T. So one of the operations between these two is T. So our result is T. So these, in the next case, both are false. Our result is false. Like that. The truth table, this is the OR operation here we are having. the truth table for PRQ also written as PRQ. We can represent like this also, P parallel lines. Next R P plus Q. This is similar to our operation addition. In addition operation, we are having 1 plus 1 equal to 1, 1 plus 0, 1, 0 plus 1, 1, 0 plus 0, 0. Like that. How we are performing one addition operation on two statements. This is the similar to that one. This is about the logical disjunction. Logical disjunction, that is the tabular form, that is the truth value. In this we are having one example. P and Q are the two statements. The P statement is, shall I go to the game? This is the statement. The next statement is, I shall watch the game on television. I shall watch the game on television. By combining these two statements, we can say that P or Q, I shall go to the game or watch the game on television. Yes, I can go to the stadium to watch IPL match, or yes, I can watch the match on television also. Here we are having the options. Yes, we can go or we can watch on the television. Just we are representing with or operation for the logical disjunction. I shall go to the game. Yes, we can go, or otherwise we can watch on the television also. Like that we can represent PRQ equal to I shall go to the game or watch the game on the television. The next one is the conditional proposition. Yes, conditional proposition. If else, that is the condition. If that statement is true, then what is the action I need to take? Like that. In the conditional proposition, if P and Q are any two statements, yes, P is one statement, Q is also second statement. This is first statement. This is second statement. P and Q are any two statements. Or the propositions also we can say that since the proposition is one declarative statement, then the statement we are representing P to Q. P to Q, which is read as if P then Q. That is called the conditional statement. If P possible, then Q also possible, like that. We are having some condition. That is the conditional statement, or the implication and the connective is the conditional connective. Here we are having that connective is just one arrow. The conditional statement here we are defining by using by following truth table. This is the truth table. Here we are having the statements PQ. PQ are the statements. We have two statements only. So 2 power n combinations we are having. 2 square. This is the number of propositions. So 2 square. 2 square is 4. Yes, 4 possible combinations here we are having. The 4 possible combinations for PQ are TT, TF, FT and FF. Okay, based on those PQ values, now we need to find the conditional proposition. If both value, P value and T value are true, then our result is also true. If P value is true, then Q value is false. In that case, our statement is false. In remaining cases, if P value may false, then Q value true. Then in this case, the resultant is T. If both are false, then our result is true. So this is the conditional statement. In this case, we are having only the false value, yet the value of P is T, truth value of P is true, and truth value of Q is false. In that case only we are having the result as F. In remaining all the cases, we will get the result as truth value as T only. Some of the alternative terminologies used, if P then Q. If P value, P to Q can also be represented. P implies Q also, we may say. P only if Q, P only if Q. If P then Q. Yes, like that we can say any of the terminology for our problems. And Q if P or Q when P also we can represent. Q follows P or Q whenever P, like that. These are all the different terminologies to express conditional operation, conditional proposition. Yes, Q is necessary for P, or necessary condition for P is Q. Like that, Q is the consequence of P. We can use any of the terminologies to express P to Q. The next one is conditional table. This is the conditional table. Just we have completed this one. The conditional table, based on the conditional table, here we can define the terminologies converse, inverse, and contrapositive. What do you mean by converse? Converse means we know P to Q is one conditional statement. Okay, based on that conditional statement, we can also say Q to P. It is called the converse statement. Just for our regular expression, we are saying contrary. Conversely, we are expressing the sentence. That is, first we are expressing Q and next we are expressing P. So that is the converse proposition. The next one is negation of P to negation of Q. Here we are having in both the cases negation. So this type of sentence we are calling it as the inverse. We are doing inverses. Next one is the contrapositive. Just for this sentence, Q to P. This is the converse sentence. For that converse sentence, we are just adding negation. So that is the contrapositive. Yes, the truth table for Q to P is the converse of P to Q. Converse of P to Q. In our regular problem, we know what are the values of P to Q. Here we are having PQ. In P to Q, the value is true. The value is false in only one condition, when the value is T and F. In this case, we are having false condition for P to Q. This is T and this is also T for P to Q. Yes. Now we are calculating the converse for the P to Q. Its value is Q to P. In this Q to P, just we are Q value. In this Q value is T and P value false. In this case only we are getting the result as false. In remaining all the three cases we get the result as true, 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 like that only. How? Here we have P to Q value. Just we are conversing. In place of P, we are placing Q. In place of Q, we are placing, see here, this is the P value, this is Q and this is P. Yes, TT, TF, FT, FF. Yes, these are the truth values for our problem. Now we are finding Q to P. The only case, this is the only case, T to F, if we are having the TF. In this case only our result is false. Remaining all are true, true, true. These are the values. Yes, in the table, Q value is, in this case, T. P value is F. In this case only, our result is false. In remaining all the cases, our value as T, T, T only. This is the converse. The next one is the inverse. Inverse means negation P, negation Q. Okay, for that purpose, we need to calculate the negation P and negation Q values. How we can calculate? Negation P, we know P value. If P value is T, then negation P value is false. If P value is false, then negation P value is T. Like that we can say. Similarly, in this table, we are calculating negation of P to negation of Q values. For that purpose, here we are having the two propositions. Two propositions are PQ is one proposition. Okay, if the value of P is 2, then value of the negation P is also T. If the value of, here we are having the two propositions. For the two propositions, two square values, we need to have 4 combinations. So, TT, TF, FT, FF. These are the possible combinations for PQ values. Next, we need to find out the negation P and negation Q values. Negation P means if the value of P is true, then negation P is false. If the value of Q is true, then its negation is false. If the value of P is T, then its negation is false. Just we are negating the sentences. If the value of Q is false, then its truth value negation of Q is T. Similarly, if the value of proposition P value is F, its resultant value of the negation P is T. For Q also, if the value of Q is T, then its negation is F. If both are F, then its negation are TT. If the proposition P is false, then its truth value is T. If its proposition Q is false, its truth value is T. Yes, we have negation P value, negation Q values, F. Okay, P to Q. Now we are just applying negation P to negation Q. Okay, in that case, just we are having the combination of only one combination we need to oppose, that is TF value. Yes, here we are having FF, we can place it as T. For FT also, we can represent with T in our solution TF. If the value of the negation P is true and the value of the negation Q is false, in this case only our result is F, false value. If both are 2, then our result is also true. Like that. This is the truth table for inverse of P to Q. Next one is the contrapositive. Contrapositive of P to Q is negation P to negation Q. Just we know how we can complete negation Q and negation P. Okay, just we are changing the locations. Just we are flipping in place of negation P, we are flipping it Q. Negation Q in place we are replacing with negation P. Like that in this table. P to Q, this is the negation Q and negation P. Only the case, if the value of the negation P is T, if the value of negation Q T and negation PF, this is the only case, the result value will be F. Otherwise, we may get the result as true. In all the cases, this is true. These two are the true cases. We know how to find negation P and negation Q values. If the value of P is T, then negation P is F. If the value of P is F, negation P is T. Similarly, for Q also. If the value of Q is T, its negation of Q is F. If the value of Q is false, negation Q is T. And like that we can represent. Here we are combining the two statements P and Q, TT. Okay, if it is T, then it is false. If it is T, then its value is false. The value of P is true. The value of negation P is false. The value of P is false and its value of negation P is true. If the value of P is false and its negation is T. And like that for Q also. So this is the truth table for negation Q to negation P. That is the contrapositive of P to Q. In this we are having the 4 type of solutions. The first one is P to Q condition. P is conditional to Q. The next one is Q to P is 1. The next one negation P to negation Q. The next one is negation Q to negation P. This is our regular expression. Okay, further this is the converse. This is the contrapositive and this is the inverse. Like that. We are having the 4 different types of notations for our conditional statement. Yes, converse, contrapositive and inverse. Example, it is raining, the crop will go. The implication formula is P to Q states that if it rains, then the crop will grow. Yes, if it rains, then the condition, here we have. If it rains, then the crop will grow. The converse of the implication is, that is Q to P. If the crop will grow, then there has been rain. Yes, this is also true. The inverse of the implication P to Q is negation of P to negation of Q states that if it does not rain, If it does not rain, then automatically the crop also will not grow. This is the statement. The contrapositive of the implication P to Q is negation Q to negation P. That states that if the crop do not grow, then there has been no rain. If there is no rain, then the crop, it don't grow. Like that. The condition here we are having only the two statements. PQ are the statements. Okay, based on these two statements, we can represent in 4 different ways. This is, if it rains, then it will grow. If the crop will grow, then there has been rain. If it does not rain, then crop will not grow. If the crop do not grow, then there has been no rain. Like that we can represent. Yes, I followed the textbook for all these content. That is, our regular textbook is JP Tremblay Manohar Discrete Mathematics for Mathematical Structures with Applications on Computer Science, Tata McGraw-Hill Publications. And reference books are Kenneth Rosen Discrete Mathematics and its Applications. Web references are Geeks for Geeks. Yes, and Mathematics for Computing, one PDF textbook is there. I collected all this content from all those. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.